Okay, so now we're back with electron configurations. And this is all about figuring out where within all of these different orbitals our electrons are. And it gives a good description of where they are. Okay, so what we're reliant on is the quantum numbers that we've previously talked about. We've talked about the N, L, M sub L, and to a little bit lesser of an extent is that M sub S. We're not really going to worry about that M sub S for the time being. What you need to know about the M sub S is it has a value of plus 1.5 or plus 1/2 or minus 1/2. So think about it as, or I think about it simply as positive or negative, but I always do have to remember that it's plus 1/2 or minus 1/2. Okay, we're reliant primarily on that N, L, and M sub L. Now, what is an electron configuration? Electron configuration describes the way in which the electrons are distributed among the various orbitals. Okay, so let's take, for instance, hydrogen. Where is hydrogen on the periodic table? Hydrogen is the very first element that you talk about. Okay, now, here's my very rough depiction of a periodic table, and here we go, there we go, there we go. That's a very rough depiction. There's hydrogen right there. Okay, now hydrogen is in the first column and in the first row. So what is the placement of that atom on the periodic table, or that element, tell us about any of our quantum numbers? One, our N value is 1. Okay, so we have N equals 1. Okay, now what can we figure out about that? Well, can we figure out our L value? Or what our L value could possibly be? Our L value is 0, or could be 0 up to N minus 1. Those are the possible ranges for our L value. So if we know that, does that give us any information on what our L value is based on our N value? Well, could L equal 3? No, it couldn't. Could L equal 1? Our N equals 1. L can possibly equal 0 all the way up to N minus 1. So let's plug our N value in right there. What's 1 minus 1? That's 0. So 0 is our L value. So we're dealing with, right now, N equals 1, L equals 0. Okay, what about our M sub L value? Our M sub L value, well, that tells us, or we can have a range from negative L all the way up to 0, and then all the way up to positive L. Okay, if L equals 0, which we've already defined right here, what does that tell us about our M sub L value? Well, what's negative 0? That's 0. What's positive 0? That's still 0. So our M sub L value must be 0. Okay, now what does that information tell us about our electron configuration? What that tells us about our electron configuration is, well, basically where our electrons are, and spatially. Okay, so let's think about how many electrons does hydrogen have? A hydrogen atom has 1 electron. Okay, now if our L value equals 0, what does that tell us about the shape of our orbital? Well, think back to this. If L equals 0, we're talking about a spherically shaped orbital, or an S orbital. Okay, so our electron, our single electron for hydrogen, has to be in that S orbital. Okay, so what we would say about that is our electron configuration for hydrogen is 1s, our value, so value of our N, 1s1. That is our electron configuration for hydrogen. Okay, now, did we really even need to figure out our M sub L value? No, we didn't, but it might come in handy later. Okay, so now as you go through this, what will be very helpful is to look at the periodic table as a whole. So the periodic table as a whole And this is an outdated version of the periodic table, but the periodic table as a whole is broken into a couple of different blocks. Over here on the left-hand side of the screen, you'll see these green letters or green numbers appear. Now these green numbers right here, what do they correspond to? They correspond to our n values. Okay, so that principal quantum number. Okay, now the periodic table can be organized in a couple of different ways. So one way is that you could look at this entire region right here of the periodic table and define it as your S block. Okay, so electrons there are going to be placed in the s orbital. Okay, the next grouping, I'm going to highlight this over here. This is known as your p block. And then the final grouping is this chunk in the middle. And this chunk in the middle, these are our transition metals, but this is also known as our D block. Okay, now when you organize the periodic table in that way, it's kind of helpful because it gives you a mechanism to kind of organize your thoughts about where those different electrons are. Okay, now what I'd like to do is give you a little bit more terminology that you'll see from here on out. And that terminology, oh, sorry, and then finally the F block. But like I said previously, we're not really going to talk about the F block very much. So the last bit of terminology, or there's a little bit of terminology that we need to get hammered away, and that is the designation between an electron shell, which is a collection of orbitals with the same value of n, and so that same principal quantum number, and then underneath those shells are subshells, which are just different designations. So kind of a shell would be all orbitals that have an n equals 2. Well, that n equals 2 can give the value of L equals 0 or L equals 1. So these are examples. So what that ultimately leads to is the 2s orbital and the 2p orbital. Those are examples right here of subshells. And the shell would be n equals 2. Okay, so now when looking at the periodic table and writing electron configurations, this is a very good way to approach things. And this is a very helpful way to kind of organize your thinking. Now, we've got our S block over here on the left-hand side. We've got our P block over here on the right-hand side, the D block in the middle, and the F block down on the bottom. Now, I think that it's maybe most helpful to just jump right into some examples. Okay. Now, so I've got the periodic table here, and I want to use that as kind of a reference for us. This has all of the different blocks defined. This was seen on the previous slide and in the previous bit in this video. We've got the 1s orbital, the 2s orbital, 3s, 4s, 5s, 6s, 7s, 2p, 3p, 4p, and so on. So we're going to kind of walk through some different examples here. Now, those examples are just as we move across the periodic table. So the first element that we're going to talk about is the electron configuration for hydrogen. We've actually already done this, and that is hydrogen has an electron configuration of 1s1 because we have one electron, and that one electron is in that 1s orbital. Now helium, where's helium? It's over here. Okay, so helium, we've got 2 electrons. Where are those electrons? Let's think about building an atom. We've got, at the center, we've got our nucleus, and then we've got this ring outside of here that can hold how many electrons? It can hold 2 electrons, maximum. After that, we've got to go onto a bigger ring and so on to put those next electrons. But in the case of helium, where are those first 2 electrons? Those first 2 electrons are in the 1s orbital. So an electron configuration for helium is 1s2. Okay. Now, what does this mean? This shows us that our 1s orbital is full. We've only placed 2 electrons there, and that's all that we could place there. Okay, so then if we jump over to lithium, well, lithium has a total of 3 electrons. And again, we're doing the exact same thing. We're building this atom. We're placing these electrons lowest energy to highest energy. We're placing them out from our nucleus. So the 3 electrons of lithium, where did the first 2 go? Well, those first 2 are going to be the exact same as the first and only 2 in helium. So we're going to have a 1s2, and then what we're also going to have is we're going to place our third electron. Our third electron is going to be outside of the 1s orbital, and that's going to be found in the, well, 2s orbital. So 2s1. Okay, so as we go, we've got one sphere. I always kind of think about it as the nucleus is just this infinitesimally small space, and outside of that, we've got like let's say a baseball. Okay, and that baseball has 2 electrons, the first 2 electrons. That baseball corresponds to the 1s orbital. Okay, now the next orbital that we can fill is the 2s orbital. That's going to be slightly larger than a baseball. So I was thinking about it like a softball or something like that. Okay, and we can put 2 electrons in that same softball shape. Okay, so that's helpful when we talk about beryllium, because beryllium has 4 electrons. We've got the first 2 in that baseball, the next 2 in that softball. Okay, now what that means is right there we've got our 1s and our 2s orbitals filled up. If we jump down, or when we jump down to boron, well, we've got the exact same electron configuration, 1s2, 2s2, okay, but boron has a 5th electron. That 5th electron is going to be over here in the 2p orbital, 2p1. Okay, now let's just take a moment to step aside from that. When we talk about principal quantum numbers, boron is in the second row here. Okay, so what is our n value? Our n is equal to 2. Okay, now what does that mean for our L value? That means that L can have a value of 0 or 1. Okay, now what does that L value tell us about the shape of an orbital? That L value tells us if L equals 0, we're talking about a sphere. If L equals 1, we're talking about a dumbbell. Okay, and that dumbbell can be in 3 different orientations about the X, Y, and Z axis. Okay, so those 3 different directions, those are going to come from our M sub L values. But ultimately, what that means is that, so we've got our L equals 0 is our sphere orbital, our S orbital, and L equals 0 is our sphere, L equals 1 is our p orbital. Okay, so we've got a 2s2 and a 2p1 orbital, and we put 1 electron in there. Okay, next up is carbon, which is going to have 6 electrons. It's 1s2, 2s2, 2p2. Nitrogen, I'm just going to fill these all out and not go through the breakdown of all of them. I think that this is helpful because ultimately you begin to see some trends. So 1s2, 2s2, 2p3. Oxygen has 8 electrons, 1s2, 2s2, 2p4. If you add up your exponents, well, that's when you're going to see the total number of electrons that you're placing. Fluorine has 9, neon has 10, 1s2, 2s2, 2p5, and then finally 1s2, 2s2, 2p6. Okay, so that's the rundown of all of these different atoms and all the different electron configurations. Now, as you continue on down the periodic table, you follow those same sorts of trends. There are some outliers, but more times than not, you're going to be just fine following those trends. Okay, so stability of electron configurations and stable electron configurations exist when the s and p orbitals of an element are going to be filled. And that's maybe best displayed whenever we look at helium, neon, and argon. Now, if you think about where those are on the periodic table, those are all going to be noble gases. So helium has an electron configuration of 1s2. So we've got that s orbital, that s subshell filled up. Okay, neon. We just did the electron configuration for neon. 1s2, 2s2, 2p6. That p orbital, that second p orbital, is completely filled up. Argon, well, that's going to be 1s2, 2s2, 2p6, 3s2, 3p6. Krypton, oh, I'm blocking a portion of it, but the only portion that I'm blocking there is the, I'm going to rewrite this, 4p6. Okay, so that goes 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p6. Okay, so all of these are examples of very stable elements, electron configuration. These are examples of stable electron configurations. And one of the first things that we talked about, or one thing that we talked about earlier this semester, was the overall stability of noble gases. And those noble gases attain that stability because they have full s and p orbitals. And so you can kind of think about any electron or any atom as reaching a level of stability whenever it fills those s and p orbitals, or s and p subshells. Okay. Now, last two definitions before we go on, and those are your valence shell. Your valence shell is the outermost shell, the electrons furthest from the nucleus and therefore the most weakly held. Those are also the highest energy. Okay. Your valence electrons are the electrons in the valence shell. These are the ones that are going to be gained or lost. So think about them as being gained or lost in the form of forming an ion, whether it's a cation or an anion. If you're forming a cation, what's going to happen? You're losing an electron. If you're forming an anion, you're gaining an electron. You're gaining a valence electron. Sorry for the lengthy video, but thank you very much. I hope you have a good afternoon.